Hello. This is Nicholas. In a couple of videos ago, I gave a not so rigorous way to check for linear independence of solutions. And I basically just said, well, if they don't look the same, then or if one isn't a scalar multiple of the other, then they are linearly independent. And I want to provide a more formal way for checking linear independence between solutions. And this way, it comes from the Wronskian, I think that's how you say it, the Wronskian matrix. And the Wronskian matrix is a square n by n matrix, and it looks like this. We have n functions called y sub 1 of t, y sub 2 of t, y sub n of t. And we go down, we take the first derivative, we take the second derivative, we go down, we take the up to the n minus 1th derivative. And we go through and we do that for every function, and that's what the Wronskian, the general n by n Wronskian would look like. So from linear algebra, remember that if two columns of a matrix are linearly dependent, then their determinant is 0. For example, if I have the matrix 1, 2, 2, 4, this I'll call column 1, and this I'll call column 2. Well, column 2 is just 2 times column 1, and the determinant is 0, and you can check 1 times 4 minus 2 times 2, that's 0. The actual reason why that is because the determinant, at least in the two-dimensional case, when the matrix is a 2 by 2, it gives the area of some generic region in space that is changed after this matrix is viewed as a vector transformation. So what did all I just said? What did all that just mean? It means let's consider the basis vectors. Okay, we have I and j hat. And so I hat now is going to be moved from 1, 1 to 1, 2. So 1 over and then 2 up. So it'll be like that. That's I hat. And I'll do it at a different hat. Now j hat is going from 1, 1 to 2, 4. So 2 here, and then we go up 4. So there's j hat in red. And so I hat and j hat are lying directly on top of each other. So the area enclosed by the two is 0, and that's why their determinant is 0. That's the geometric meaning of the determinant. It measures the area of some generic region in space after the vector transformation given by this matrix is applied to the space. And so if the determinant is 0, then the two, if we're in the two-dimensional case, then the two vectors are lying on top of each other, and that means that they're parallel, and if two vectors are parallel, then they can be written as scalar multiples of one another. In this case, j hat, I'll just call it j, because it's not a unit vector anymore. The vector j is just 2 times the vector I, or not I hat, just the vector I. And so they're linearly dependent. So the easiest way to check for linear independence of two solutions, if you've got 2, for example, call them y sub 1 and y sub 2 of t. So you take the Wronskian, and based on this general form, the matrix will look like this. So we just have one derivative. You take the Wronskian, and you want to check whether this column and this column are linearly independent. In other words, you want to see, if this is column 1 and this is column 2, you don't want I'll call it column sub 1 to be c times column sub 2, where c is just some constant. that would imply linear dependence. So if we actually, evaluate this determinant using the formal, the definition that you're used to, so we do this minus that, and I'll just write y sub 1, y sub 2 prime minus y sub 1 prime y sub 2. I'm not going to write of t. And we don't want this to be equal to 0. We want the solutions linearly independent. And if they're linearly independent on some interval I, which say is from A to B, then the Wronskian will never be 0 on that interval from A to B. And if we have this as our determinant, then this implies, so then that would mean y sub 1, y sub 2 prime cannot be equal to y sub 1 prime, y sub 2. And that would imply that y sub 1 cannot just be some constant times y sub 2. If it were, then what would happen is, so say y sub 1 is equal to cy sub 2, then cy sub 2, y sub 2 prime is cy sub 2 prime y sub 2. And so those things are equal to each other, and so there's linear dependence. So this is how you can check for linear independence of solutions. For example, take maybe y sub 1 of t is t cubed, and y sub 2 of t is e to the 2t. So we have 3t squared and 2e to the 2t. We can differ, or not differ, we already differentiated. We can get the determinant, which would not be written with the brackets, it would just be with the lines like this. That's 2t cubed e to the 2t minus 3t squared e to the 2t. And so what we could say is that, we could make it e to the 2t times 2t cubed minus 3, minus 3t squared. And we're going to be looking at when this is 0. This is never 0, so we can just get rid of it. So when is 2t cubed minus 3t squared equal to 0? So we can have t squared times 2t minus 1 equals 0. So t is equal to 0, or t is equal to a half. And if we do like a sign chart or something on this polynomial here, this right here, we have 0 and we have a half. If we plug in a bajillion, a really big number, we're going to be positive. If we plug in a really small number, we're going to be negative. And if we plug in something like somewhere between 0 and a half, let's say a fourth, 2 times 1/4 cubed, that's 2 times 1 over 64, minus 3 times 1 over 16. Is that going to be positive or negative? That's 1 over 32 minus 3 over 16. And so that's going to be negative. That's going to be a negative number. Yeah. So we have negative, negative, positive. So this is saying, why did I construct this sign chart? I constructed it because what we can now conclude is that, it's 0 at exactly, at exactly 1/2, and at 0 as well. So we can say that on the interval from 1/2 to infinity, that these solutions are linearly independent and they form a fundamental pair of solutions. And we can say that from 0 to 1/2, they're linearly independent. And we can say that from negative infinity to 0, they're linearly independent. We cannot say, for example, that they're linearly independent from negative infinity to infinity. because they're not. At 0 and at 1/2, they are linearly dependent. That's why the determinant would be 0 at those two particular points. But if you consider this separate interval, this separate interval, or this separate interval, or a union between the three, then the solutions are linearly independent. And I think that really pretty much sums up the Wronskian. Maybe just some notation. This way I wrote it here, it's more compactly written as the Wronskian of y sub 1, comma, dot, 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 comma, y sub n. And then these are all functions of